So, we've talked about energy in general using Q is equal to MC delta T, but we're in chemistry, so we want to deal with reactions. So we're going to be using kind of a teeny tiny bit of stoichiometry today. Kind of a teeny tiny bit. Bless you. So the process that we're going to be using is we're going to balance our reaction, because anytime we're doing anything even partially associated with stoichiometry, we need a balanced equation. The second step, we're going to determine moles. So I need to determine how many moles I have. And then whatever I end up calculating, I need to determine if it should be positive or negative. If my enthalpy is related to releasing energy, so something that's exothermic, then I'm going to have a negative enthalpy. Sometimes that negative will already be there. Sometimes I need to read through the problem and see if it's going to be negative, and then put that in. If energy is going into the system, it's endothermic, so I'm going to do it as positive. Energy is positive. Few more seconds. There's a few pens going still. Okie dokie. So, our first problem here. We have 1 mole of SO2 reacting with excess O2 to form SO3 at constant pressure. And for that 1 mole, 198 kilojoules of energy is released as heat. We need to calculate the delta H for the process in which we have 12.8 grams of substance, SO2, reacting. So let's pull this apart. First thing, we need a balanced reaction. So SO2 reacts with O2. Those are my reactants. It tells it to me right there. So I'm going to start out by writing SO2 plus O2. And it says it forms SO3. So I do my arrow, and my product is SO3. Go ahead, try to balance that one on your paper. Please do not shout anything out. Okay, show me with your hand what number we would put in front of the SO2. Show me how many fingers. Excellent. I see a lot of 2s. 2 SO2. Show me again using your hand what number we would put in front of SO3. Nice. Another 2. So now I have a balanced reaction. So that's my first step always. Now I can start pulling this problem apart a bit. So it says that 1 mole of SO2 gives me this much energy. So I'm going to write out that conversion, because it's always good to write out what I know. 1 mole of SO2 is equal to 198.2 kilojoules. I also know that 1 mole of SO2 is equal to a certain amount of grams of SO2. Go ahead, point to me where in the room I can figure out the mass of SO2. Excellent, you're all pointing to the periodic table. That is absolutely correct. So, look at your periodic table and figure out what mass I'm going to put down. Yeah, 64. 64 grams of SO2. This will be all that I need to solve my problem, all of the conversions that I need. So first of all, I need to determine what my given is, because I always start with my given. And that is right here, 12.8 grams of SO2. So given is equal to 12.8 grams of SO2. Again, I always start with my given in any of these conversion problems. So I'm going to start with 12.8 grams of SO2. I want to get rid of grams so that I can get to moles, so I'm going to use my bottom equation. I put 64 grams of SO2 on the bottom, because then I can cross off with this grams of SO2 that I had at the top of my reaction. Whenever I deal with a mass from the periodic table, that's the molar mass, so 1 mole of that thing goes on top. It's always 1 mole, nothing else, always 1. And then I can see from my first reaction, or my first value here, 1 mole of SO2 is equal to 198.2 kilojoules. So I put what I want to get rid of on the bottom, that's 1 mole of SO2, which cancels out with my top here, mole of SO2. And then on the top of this fraction, I put 198.2 kilojoules. I'm going to get a value in kilojoules, which should be good because I'm looking for a delta H value. It's not asking me to convert like our starter question did. So all I do is 12.8 multiplied by 198.2 divided by 64. And I need, let's see here, 3 sig figs. 3 sig figs for this one. Do you have it, David? Perfect. 39.6. Thank you. 39.6. Now the last part of that last slide said that I need to figure out if it's exothermic or endothermic. So would I have a positive or a negative here? So I'm going to go back to my problem and read it again and look for any key words or phrases that makes me decide what it is. It does say release. Thank you, Duncan. So what does that mean? Exothermic, excellent, Charlie. So what should my sign be? Negative, excellent. I didn't hear who said that. Thank you. Negative 39.6 kilojoules is my final answer for this one. Again, we're just doing some dimensional analysis, some factor label method. I always start with my given. I always cancel out what I want to get rid of by putting it on the bottom, put what I want on the top, until I get the final unit that I want. Questions so far? Cool, we'll do the next problem then. So, we have this reaction in most heat packs that are used to treat sports injuries. So if you're out on the field and the coach pulls out one of those packs from their first aid kit and cracks it and shakes it up a little bit, this is the reaction that's going on. So we have some iron reacting with some oxygen, forming iron 2 oxide, and that releases, it's already given to us right there, it's releasing negative, it's releasing 1,652 kilojoules of energy that you then use to treat wherever you hurt yourself. We want to know, though, if we have 1 gram of iron in our little bag, how much heat's going to be produced. Right now, we know that 4 moles of iron are going to give us this amount. So our conversion factors are slightly different this time. Last time it said, let's go back, it said for 1 mole of SO2. This time I have to look because it doesn't tell me specifically for 1 mole. It tells me for this reaction. So I need to look at the one that I'm looking at, which is iron, and see the value up front, because that's always the number of moles. So here my conversion factor is 4 moles of Fe is equal to this negative 1652 kilojoules. I also know that 1 mole of Fe is equal to a certain number of grams of Fe. We're going to look the same place we looked before. And let's do it with 4 sig figs. I know the periodic table we have up there has 5. Why don't you give it to me in 4? 58.85. 55.85. 55.85. Thank you. These are the conversions I will use for this one. So I start out with my given. What's my given? Yes, 1 gram of Fe. Thank you. 1 gram of Fe. I want to get rid of grams, so I put 55.85 on the bottom. How many moles do I put on top? Shout it out. 1. Good. Thank you. And then, I look here, I want to get rid of moles of Fe, and I need to use this value from my coefficient. 4 moles of Fe will go on the bottom. And on the top will be my energy value, negative 1652 kilojoules. Ooh. So I can double check my units. Grams of Fe cancel out because one's on top, one's on the bottom. Moles of Fe cancel out because I have 1 on top, 1 on the bottom. I'm going to end up with kilojoules, which is a good unit for energy. It's not asking for it in joules, so I don't need to make any conversions. And we need just 1 sig fig this time. Look at that, 1 gram. 1 gram means 1 sig fig. So I want my answer in 1 sig fig. I'm going to let you calculate it here. Please do not shout it out. Gonna give you about 30 more seconds. Finish calculating it. Then I'm gonna ask you to show me using your hands. Not yet, but soon. Okay, show me using your hands what value we get in kilojoules with 1 sig fig. Excellent, I see lots of 7s. That is beautiful. 7 kilojoules is our final answer here. Lovely. Excellent. It is exothermic. Perfect. Good, Anna.
I'm kind of confused because didn't it already give us the amount of heat that was released with that, negative 1,652 kilojoules? Like, I'm kind of confused.
When we have 4 moles of iron, but we started with 1 gram of iron, which is not the same as 4 moles. Good question. How we get what part? Yep, so you should be able to type into your calculator negative 1652 divided by, and then what I would do is put in parentheses the 55.85 times 4, and then that value should give you a negative 7. I know it looks like we're done, but I want to tell you one last thing that is going to help you with question 5 on worksheet 1, because I told you you couldn't do that yet. You're going to be able to do it now, and that's going to be part of your homework tonight. Worksheet 2 and question 5 on worksheet 1. So question 5 on worksheet 1, requires the following information, which is also on the board here. Delta H is equal to the products minus the reactants. So pull out your worksheet so you can see what I'm talking about. It says the standard enthalpy change for the formation of Al2O3 is negative 1669 kilojoules per mole, and the standard enthalpy change of the formation of Fe2O3 is negative 822 kilojoules per mole. Use the values to calculate delta H at standard enthalpy for the following reaction and state whether the reaction is exothermic or endothermic. Notice that elements that are not bonded, have 0 bond enthalpy. Makes sense, right? There's no energy related to bonds because there is no bonds. So what parts of that equation can we ignore? Yeah, aluminum and iron. The Al and the iron. The Al and the iron. So we ignore those parts. And we look at our balanced reaction, and we see that for each of the ones that are actually bonded to things,